Hello, everybody, and welcome back to Learning Calculus. Today's topic is the application of and using derivatives. For a quick introduction and why I'm qualified to teach you some calculus, I think that math is fascinating. And I just recently graduated and I earned a 5 on the AP Calculus BC exam, which is equivalent to Calculus 1 and Calculus 2. And when I grow up, I plan to teach calculus or a math class when I grow up. And remember, the best way to improve at calculus is by doing calculus work. Okay, so today's agenda is also going to be long, just like the last episode. We're first going to go over the extreme values of functions, and we're going to talk about all sorts of things: critical points, endpoints, candidates test, first derivative test, and the second derivative test. And then we're going to compare f of x, f prime of x, and f double prime of x in just a broad overview. And then we're going to talk about some existence theorems. So we've already been over the intermediate value theorem, and then we're going to introduce a couple more today. We have the extreme value theorem and the mean value theorem, and then Rolle's theorem, which is kind of a type of mean value theorem. And then let's go over some problems. We're going to go over linear approximations, modeling optimization problems, and then related rates problems. And those are all types of problems that you'll see really commonly where stuff like this comes into value. Okay, perfect. So let's talk about extreme points and critical points. So lots of important information can be learned from a graph and its derivative. You can talk about the maximum and minimum points, and that's important because it tells you valuable data about a graph. And knowing when the function's value is increasing or decreasing also helps us analyze functions better. So to see why critical points are important, take a look at some of these graphs with maximums and minimums in it. And let's take a look at some commonalities between them. I'm going to point out right now that the two things that are common between them is that the slope of the curve is 0 when you're at a maximum or minimum, and the slope of the curve changes from positive to negative when you reach a maximum. So let's take a look at some examples. Let's take a look at g of x right here. And this point right about 1.5 is going to be your minimum of the function. And as you see, as you come into the derivative, as you come into the minimum, the extrema, as you come into this extrema, your derivative is decreasing and you're decreasing. And at the moment you hit the minimum point, it has decreased all the way to 0. And then as you start leaving from the minimum point, your derivative starts increasing and you start going into more positive slope. And then the same thing can be said for h of x. So let's look at the relative maximum point for h of x, which is at about 1. And as you go into this maximum point, your derivative slowly decreases until you reach 0. And then it starts becoming more and more negative. So extreme values happen at critical points. And then here's the definition of a critical point. So let f of x be defined at a point C. If f prime of C equals 0, or if f prime of C equals does not exist, C is a critical value. So that means that there is some sort of extreme value happening at the point C. So if f of x is a continuous function on the interval a to b, f of x must have a maximum value and a minimum value on its interval. And boom, we already did it. That's the extreme value theorem. It's really easy. But when we're thinking about critical values, using the extreme value theorem, we know that they must exist on an interval. We can use what's called a candidates test to find critical values. As I say right here, using a function as its derivative to find extreme values and critical values is important for real-life optimization, which we'll talk about later. In order to find extrema, use a candidates test. So, and as a quick little aside, at least for the AP tests, a candidate test works as a justification for finding extrema. So if you find a problem and it says justify your answer, you can say I justified my answer with a candidates test, and you can show that as your work. So to use a candidates test, you find the critical values, and as we went over on this last slide, critical values happen when the derivative does not exist or if it equals 0. So you take the derivative of a function, set it equal to 0 or does not exist, and then you identify the endpoints of the interval. And this is really important. Endpoints are also candidates for a candidate test because they can also be extrema. If you think about, the function could jet off super duper high or super duper low right before ending the interval, and you wouldn't know because you never actually reach a minimum point. So once again, endpoints are always also candidates. And then you just evaluate f of x at each critical number and the endpoint. And then whichever is the highest will be a maximum, and whichever is the lowest is a minimum. So let's take a quick example problem where you use the first derivative to find critical values and then use a candidates test. So the problem says the rate at which gasoline flows out of a storage tank into trucks at time t can be modeled by the function r of t, which is this rational equation right here, where t is modeled in hours and r of t is modeled in thousands of gallons. Based on the model, at what time t for the interval 0 to 10 is the rate at which gasoline flows out of the storage tank at an absolute maximum. And then it says to justify your answer. So with my really crappy drawing on Microsoft Paint, our first step is to find the critical values of r of t. And this is once again because critical values are always going to be maximums or minimums. So when we take the derivative to find the critical values, it ends up looking like this. This is your quotient rule, if you remember from the last episode. And let's think about a couple of things here. So we need to know when r prime of t is equal to 0 and when r prime of t is not existing. This is a rational function, so it is possible for it to not exist. But because of how this rational function is written, I'm going to say that it's a safe bet that nothing, it does not exist, if that makes sense. And this is why. Normally when something doesn't exist, that typically means you're dealing with a divide by zero error. And that's especially true when you're dealing with a rational function. Divide by zero errors make your problem not exist. But because the bottom has two aspects of it, first of all, t is squared on the bottom. So that means that no matter what value you plug in as t, it's always going to be a positive value. And then even further, it's being added by 4. So even if you plugged in 0, so 0 squared is 0, you're always going to be adding 4. So that means that you won't ever have an area where t does not exist. So the function is never going to not exist. And then let's talk about when r prime of t equals 0. Once again, when dealing with a rational function, when something equals 0, that typically means that the top of your rational function equals 0. So let's run with that. Let's set just the top of the equation equal to 0, and let's solve for it. So here's the process right here, all written out, and you find that t is equal to 2 and negative 2. As a quick note, because the interval is 0 to 10, negative 2 cannot exist as an answer. Also, just thinking about it logically, you'll never have negative time. So the only answer will be at 2 hours. So t equals 2. And then let's run on to the second part of the problem where you use a candidates test. Remember, one of the really important things about a candidates test is that you use the endpoints of the interval. So you also are going to have 0 and 10 as candidates. So our candidates are 0, 2, and 10. And to use a candidates test, once again, you just plug them back into the original equation. So not r prime of t, just r of t. And when you do that, you find that 2 is the maximum value. So then you can say something like this. The rate at which gasoline flows into the tanker is at its absolute maximum when t is equal to 2. And then I would even write r of 2 is equal to 25, because sometimes you might misread the problem and you might need the value that is the maximum. Sometimes it asks you when the maximum happens. Sometimes it asks you what the maximum is. So it's always a really good habit, I think, to write the full answer. So r of 2 is equal to 25. Okay, let's talk about the first derivative test. So the first derivative test is really easy. You let c be any critical number on the function f. which is continuous and open, containing C. So if f is also differentiable on the interval, except at C itself, once again, remembering that critical values may not exist, then f of C can be described as the following. So if f prime of x changes from negative to positive values at the point C, f of C is a relative minimum. And let's take a look at why. So here's this little graphic showing this idea. And your values of f prime of x are decreasing right here, or sorry, below 0. They're negative. It means that your slope is down. And as your slope is going down, 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 and down, you eventually, as we've been over, reach the point where the derivative is equal to 0. So it's a critical value. And then it starts increasing. And because of that fact alone, we know that f of C is a relative minimum. And then the same can be said for f prime of x. When it changes from positive to negative at the point C, f of C is a relative maximum. With this, I like to think of mountains and valleys. When you're going to the top of a mountain and then you hike back down, you can think of the mountain as a maximum. And as you climb up the mountain, your derivative, your slope is positive. And then once you reach the top of the mountain, you stop moving. And then you start going down the mountain and your slope is negative. And then the same can be said for valleys. As you travel down into the valley, your slope is negative. You're decreasing into the minimum point. And then once you reach the bottom of the valley, there's nowhere to go except upwards, and you start climbing back up with positive derivative. And then as a quick note, if f prime of x does not change signs, it is neither. So this can look like a flat section of your function. It won't be a maximum or a minimum, but it could be flat. Okay, so the second derivative test is a little bit more confusing because we have to talk about a couple of new ideas. So let's first talk about concavity. Concavity determines whether a graph is curving upwards or curving downwards, and it tells you about the rate of change of the slope, which we know is the second derivative. Once again, think of valleys and mountains. If concavity is up, it's like a valley. So let's take a look at right here. When concavity is up, you kind of make a little valley shape. And then concavity down is like a mountain. It's like the peak of a mountain. So here we go. If f double prime of x is is greater than 0, your concavity is up. And if it is less than 0, concavity is down. And let's take a look at these four little quadrants right here. It's really important to understand what concavity looks like and what it means for the slope. So let's take a look at quadrant 1 right here, where we can say that f of x is increasing at a negative rate. So yes, it is true that the function is increasing in value, but as you get closer to this end, the rate at which that happens is negative, and that's because it's concave down. For quadrant 2, we can see that it's concave up. So as you continue to increase in value, the rate at which that happens continues to grow positive. Once again, because it's concave up. For quadrant 3, we can say that f of x is decreasing at a negative rate. So because you're decreasing, when your rate of decrease is negative, that's actually going to make you decrease faster and faster and faster, which is why it's concave down. And then for quadrant 4, f of x is decreasing as a positive rate. I'm sure I don't need to go over this one. As you decrease in value, the rate at which that happens is slower. And let's talk about inflection points. So inflection points are when the graph changes concavity. As you see right here, it's labeled as the inflection point. It occurs when the double derivative changes from positive to negative and when the derivative itself equals 0. So if f double prime of x is greater than 0, concavity is up. If f double prime of x is less than 0, that means concavity is down. I wrote that twice because that's just one of the most important things to remember about concavity. So the second derivative test is all about concavity. If f prime of c is equal to 0 and f double prime of c is less than 0, that means that f of x has a local maximum at c. Let's go over why. So f double prime of c is less than 0. That means that it's going to be negative. That means concavity is down. And as we went over with the mountain example, Maximums are like mountains, and they do this. They're concave down. And then right here, if f prime of c is equal to 0 and the double derivative is greater than 0, so it's positive, that means that f has a local minimum at the point x equals c. And once again, think of valleys. When concavity is up, that means that you're looking like a valley, like a U shape, and that means it will be a local minimum. And then if if f prime of c is equal to 0 and the second derivative is 0 or does not exist, you have to use the first derivative test. The second derivative test won't help you there. Okay, here's a little comparison between f of x, f prime of x, and f double prime of x. I'm not going to go over all of these because we kind of did just go over all of them. Here's them summarized into a really easy to read chart. If it's visually helpful for you, here's a visual comparison between f prime, and f double prime. I drew this in Microsoft Paint, so that's why it looks really bad. Here's the key down here, and you can see, like, let's take a look at some sections. So, like, green is increasing on the original function. It's where the function slope is positive, and then that's what the first derivative shows us. Purple, extrema. So as we went over with the first derivative test, extrema happens at critical values. Critical values happen when the function is equal to 0. So as you can see, the zeros on the first derivative relate to the maximums and minimums of the original function. And let's talk about like inflection points, I guess. Inflection points are right here on the original function. It's where the concavity changes. So right here, you're concave down, concave up, concave down again, and then concave up. And that happens at the extrema of f prime of x and at the zeros of f double prime of x. So that's just kind of a visual comparison between them. Let's go over the mean value theorem. So when we first made the derivative, we started with the average rate of change of a function, and its equation looked like this, where you have f of b minus f of a divided by b minus a. So if you make a slope between the two points and it forms a secant line, the mean value theorem concludes that there is a point on that interval where the slope of f of c will form a parallel tangent line. So here we go. Let f be continuous on the function or on the interval a to b, and it's differentiable on the open interval. There exists a point c in that interval where the derivative of the point c is equal to the average rate of change. And here's a little graph demonstrating that idea. The secant line is formed between the two endpoints of the interval, and then there has to be at least some point, I'm guessing that there's two, there's going to be one right here as well, where the tangent line will be parallel to the secant line. So that means that the derivative matches the average rate of change. And here's a quick little aside, Rolle's theorem. This is where f of a is equal to f of b. This just says that if f of a and f of b are the same, then there exists a value where the derivative is 0. So this is literally just an application of the mean value theorem. It's called the Rolle's theorem. I don't know why, but it's a different theorem than MVT, but it's the same idea. Because if f and a and f of b are the same, then the average rate of change between those 2 points is 0. So let's go over a quick review of the existence theorems we have so far. So the intermediate value theorem is really easy. If your function is continuous, there has to be one point on an interval where, let me reword that. There exists any value w between f of a and f of b on the interval a to b. So you have to reach every single y value at least once. And then the extreme value theorem, if f of x is continuous, f of x contains both an absolute maximum and an absolute minimum on the interval. Here's a little drawing of that. And then the mean value theorem, which we just went over, where the tangent line is equal to the average rate of change along an interval at some point. Okay, let's start solving some actual calculus problems. And there's 3 types of calculus problems generally that you will use derivatives. Obviously, there's going to be more later when you get into like differential equations, but These are the three most common problems that you'll see using derivatives in at least Calculus 1. You have linearization or approximations, where you use a function and its derivative to make a tangent line and approximate something. Here's optimization modeling problems, where you use a derivative and its extreme values to maximize and minimize things. So as you can see, all of the information we just went over is starting to come into use. Extreme values to maximize and minimize things. And then related rates, the rate at which something is happening, and you connect it to a different rate, where implicit differentiation is important here. So what we're going to do is we're going to go over all three of these types of problems, and then we're going to look at an example problem. So let's start with linear approximation. It's really easy. Looking at a tangent line, where this tangent line is labeled L of x, you can see that one thing is clear. The closer you are to the point of tangency, the line's y values will be super duper close to the y values of the curve. And then the further away you are from tangency, so let's talk about like over here, the further you are from the line and the curve. So linear approximations just use the slope to form a line. Use the point slope form of a line, which is this, and you can write it a little differently. So instead of m, you call it f prime of a. Instead of y1 and x1, you say f of a and a. And then, yeah, you solve for y. So this is the equation of x is the point you were trying to approximate, and a is a value that is super close to x. So let's take a look at an example problem to kind of understand this idea. So find the linearization of f of x equals cosine of x at x equals pi half, and then use it to approximate cosine of 1.75 without a calculator. So we're going to first start by writing the linear equation, and what you need for that is the point slope line, the point slope form of a line. And to write the point slope form of a line, you need the point and you need the slope. So let's start by finding the point. Generally, that's easier, but sometimes it'll be easier to find the slope first. So finding the point is really easy. You're given in the problem that x equals pi halves and that you want to linearize that part. So we know that x is equal to pi over 2 and that our function f of x is equal to cosine of x. Literally just plug pi over 2 into cosine, and you find your point is at x equals pi over 2, y equals 0. Okay, now let's find the slope. When you want to find the slope of anything in calculus, remember, always take a derivative. So you take the derivative, which is negative sine x, and then you just plug in pi over 2. So you have f prime of pi over 2 is equal to negative 1. Okay, so now let's plug it into the linear approximation equation. So you have L of x is equal to f of pi over 2 plus the derivative of f pi over 2 times x minus pi over 2. And then when you plug in all of your values, you can then solve it really easily to find that cosine of 1.75 is about equal to negative 1.75 plus pi over 2. And then here's in Desmos showing how close these answers are. With this linear approximation alone, you can get a value of cosine of 1.75 that is within 1,000th of each other, which is really close. That's a really good approximation. Okay, so now let's move on to modeling optimization. So once again, using calculus, finding extrema like maximums and minimums can be easy with an asterisk because these problems can be tricky sometimes. If you think about world terms like greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, least distance, this is all optimization based. Using calculus, you can find all of these, maximums and minimums, the greatest profit, the least distance, the least size, the least time, greatest voltage, whatever. Let's go over some steps for success. So number 1, you have to really understand your problem. Read it 1 or 2 times, maybe even 3. Sometimes I even draw a picture of what I'm looking at so that I can actually understand what's going on. And then number 2, decide what needs to be maximized. So you create an equation for it and you solve it for only one variable. As a quick little note, writing other equations that you can use for substitution is super helpful. And we can look at an example of that in a second. And then you take the derivative to find the critical values. And then you determine if the critical values are the maximums or minimums, and you correctly solve the problem. So let's look at this example problem. This one's a little more difficult than normal, but it's not too bad still, if you understand what you're doing. So let's read it. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches. So that's this distance right here. And the margins at the left and right of the page are to be 1 inch, which is right here and here. So what should the dimensions of the page be so that the least amount of paper is used? And once again, we know that it's supposed to contain 24 inches squared of print. So I read the word rectangular prism. I'm thinking of area. You're talking about inches squared. Let's write down the equation of area of a rectangle, which is just length times width. And in this problem, what we're trying to maximize is not the area of the paper. We're trying to maximize the area of print. So we can write this equation in a different way. I said A sub P, which means area of print, is equal to just width times length, but we wrote it a little differently. So we know that the width, with the margins that are 1 inch long on each side, we know that width is just the entire width minus 2. And then the same for length, because the margins are 1.5 inches on the top and bottom, we know that the total length will be the length for the margins will be length minus 3. And then knowing this equation right here, we know that we're supposed to solve for 24 inches squared of print. And once again, this is just the equation for print area, not the area of the page. So you can plug in 24 right here and choose which variable you want to maximize. I think that this problem will work correctly if you solve for W or for L. I personally chose to solve for the length. So you solve for length. You have L minus 3 equals that, and then you add 3 to get L equals 24 divided by W minus 2 plus 3. So now that we have one of our variables solved for, we can plug it back into the equation that we've been using for the area of paper and get a function of area in the terms of one variable. So you can see this happening right here. You plug in L equals 4L in this equation, and you get a function of area in terms of width. So using width alone, you can now find the area of a page. And now that we have this equation with our two variables related to each other, we can take the derivative. So we have A prime of W. Once again, area is now a function of W, so you can take the derivative with respect to W. A prime of W is equal to this, which is just another time where we're using the quotient rule. And then you simplify the derivative a little bit, and we're trying to find the the minimum value of width. So you use a critical value. So once again, when finding critical values, set your derivative equal to 0. So now we have 0 equals this. And as you start solving for width, you end up doing all of this work right here. And you find that width is equal to 6. The reason why you can just discard the fact that it's plus or minus 4 is because you can't have negative length. Because if you had negative 4 plus 2 is still negative 2, you can't have negative length. So width is equal to 6. And now we're really close to solving the problem. We know that one of the optimum the optimum width of this page is going to be 6. So you can literally just plug your width into the equation that we have for length and find that length is equal to 9. So we've solved the problem correctly. The paper should be 6 inches wide and 9 inches long. And then we can verify that with the area of print equation that we have, and we can plug in our optimum values, which is 6 and 9. As you do that, you find that 4 times 6 is indeed 24. So we found that the smallest page that has 24 inches squared of print is 6 inches wide, 9 inches long. Okay, let's end this video with related rates. Related rates, I personally think, are really fun. They, once again, just like optimization problems, they can be tricky. I think that they're easier than optimization problems, because sometimes those can be really difficult. And I find that related rates are typically all really similar structure. So you're given 1 or 2 rates of something happening, and then you're asked to find the rate of something else occurring at a specific time. And this is where I mentioned at the beginning of the video, implicit differentiation comes really helpful in this type of problem. So let's go over some steps for success. Once again, understand your problem, assign variables for the things that change, and label constants for things that don't change. And then know what rates exist and what they're doing to your scenario. And then you can write down the rate of change that you are trying to find and when it is occurring. And then write down any other rates that you were given. Third, you can find an equation that relates your variables to each other. Oftentimes, it is geometric. So think things like area, volume, trig ratios, Pythagorean theorem, stuff like that. And more than one equation may be required, just like optimization. And then you differentiate with respect to time, and you plug in the rates of the variables you were given, and you solve the problem. And then always remember your units and types of problems like this. Okay, here's a little example problem. This one is probably really easy in the terms of related rates. Some of them, like I said, can get really difficult, but you'll find that this one is super, super duper easy. An oil tanker spills oil that spreads in a circular pattern, which is a radius that is increasing at a rate of 50 feet per minute. And then it asks, how fast is the area of the spill increasing when the spill's radius is 20 feet? So I drew a little picture showing what's happening. Your R is increasing at a rate of 50 feet per minute. And we write this over here as the form of a derivative. So we have dr over dt is equal to 50 feet per minute. And then we're going to note at the time that that happens, which is when the radius is 20 feet. And then we're trying to find the rate of change of the area. So how fast is this area of the spill increasing? So dA over dt. If we're thinking about a circle and we're trying to find the area at which something is increasing, pretty good bet that we're going to use the formula for the area of a circle. As a quick little aside that I didn't even write down, lots of times, at least on the AP tests, they will actually give you the formula that they're intending you to use. For example, if they ask you the question about like the volume of a cylinder, they're not going to expect that you've memorized the volume of a cylinder. They're going to give that value to you. I've seen that happen on the AP tests, so I wouldn't worry about it too much. Obviously, you should know things like the area of a circle, but, you know, sometimes it's like a more complicated shape. Like, you know, you have a cylinder or you have a triangle or a cone or whatever that you're dealing with, and it's a little more difficult. So yeah. Anyways, we have our equation right here. A is equal to pi r squared. And then, as we've talked about, we take the derivative to find the rates of these things. So we find that when you take the derivative of the area function, we find that the rate of change of the area is equal to 2 times pi r. And because we differentiated r with respect to time, we tag on that little dr over dt. Once again, implicit differentiation is super useful for problems like this. Whenever you're not differentiating something that's time, you have to tag on a little dr over or dA over dt or whatever. Okay, from here, the problem is really simple. We already have the rate of the radius, and we have the time that we're solving for, so what the radius is equal to. And we've already solved this equation for the rate of change of the area. So when you plug in your values, you can solve it and equals 2000 pi feet squared per minute. So that's the rate of change of the area. If I was on a, formal test, I would write the rate at which the area increases is 2000 pi feet squared per minute. Okay, so that's the end of today's video. We went over some really important things in calculus. Um, Basically everything useful for derivatives. If you need to, watch this video again, maybe to memorize some of the important things such as critical values and extrema and stuff like that, I don't blame you. It's a really good idea because knowing stuff like critical values is super important in derivative calculus. Even in integral calculus, it comes up every once in a while. So, this is really important stuff. This video, and then the types of problems that we went over are the most common, at least for the AP test. I'm not sure about college calculus, but for the AP test, you'll see linear approximation, you'll see modeling optimization, you'll see related rates. I basically guarantee it. In fact, when I took AP Calculus BC, there was, I think, 2 or 3 related rates problems on the actual AP exam. 2 of them were multiple choice, and one of them was even on an FRQ. So really important that you know problem types like this. So anyways, yeah, once again, thank you for watching. I hope you learned something useful about like critical values, extrema. You learned some existence theorems. You learned how to use derivatives more applicably. And thank you for watching.